integration using partial fractions. Here we're going to look at how we can use partial fractions to help us integrate things a little bit easier. So if we have the integral of dx over x minus 2 times x minus 1, this is going to be a little bit tricky just to jump straight into and start integrating. So first we're just going to consider 1 over x minus 2 times x minus 1. And using our partial fraction knowledge, we know that we're going to be able to decompose this fraction into some constant over x minus 2 plus some other constant over x minus 1. We just need to figure out what they're going to be. So we'll times both sides by the denominator, so we'll just be left with 1 equals a times x minus 1 plus b times x minus 2. And with some careful picking of some x values, we can work out a and b. So letting x equal 1 will make all of this 0. So we're just going to have 1 equals, now x1 minus 2 is going to be minus 1, so we're left with minus b. So b is going to have to be minus 1. So that was by letting x equal to 1. And now if we let x equal to 2, this is going to cancel out this value here. And we're going to get 2 minus 1, which is 1. 1 times a is a, so we're just going to get a is equal to 1. So now we know that this fraction can be written as 1 over x minus 2 plus minus 1 over x minus 1. And let's go ahead and sub that in to our integral. So we know we could rewrite this as 1 over x minus 2 plus minus 1 over x minus 1 dx. And we can just go ahead and integrate these two fractions separately. So this is going to be the same thing as the integral of 1 over x minus 2 dx minus, we'll take the minus out the front, 1 over x minus 1 dx. Now the integral of the first fraction, we know that's just going to be ln of the absolute value of x minus 2, because the derivative of the denominator is just 1 and it's in the numerator, and the same for our next fraction as well. So we're going to get minus the natural log of x minus 1, all absolute valued, plus our constant. Let's look at another example. The integral of x squared plus 4x all over x minus 1 times x squared plus 4. So we know this can be broken up into partial fractions because the degree of the denominator, that's a 2 and a 1, which makes 3, and this degree is 2, and this is less than this one. So we'll consider first our fraction, x squared plus 4x over x minus 1 times x squared plus 4. And we know this is going to be able to be broken up into a over x minus a, plus now we have a quadratic factor in the bottom, so we know we're going to get a linear factor in the top, so we get bx plus c all over the x squared plus 4. And we just need to work out a, b, and c here. So again, we'll times everything by the denominator, so we'll have x squared plus 4x on the left. We'll have the a times x squared plus 4 plus bx plus c times x minus 1. So here we're going to we just need to figure out what a, b, and c are. So let's first let x equal to 1. What's going to happen is all of this is going to cancel out because it's all going to be 0. On the left-hand side, we're just going to have 1 squared, which is 1, plus 4 times 1, which is 4, so we're just going to get 5. On the right, we're going to get, again, 5 times a. So we know a is going to be equal to 1. Let's let x equal 0. That'll get rid of this b term. And we know a, and then that'll help us find c. So on the left, when x equals 0, we're just going to get 0. We know a is equal to 1 times x is equal to 0, so we're just going to have 1 times 4. Plus the b term will cancel out, so we just have c. And 0 minus 1 is minus 1. So we're going to have 0 equals 4 minus c. So c has to equal to 4. And now we can just go ahead and let x equal anything to figure out what b equals. So we'll do, let's do minus 1. So let x equal minus 1 this time. So we'll get, on the left-hand side, we'll get minus 1 squared, which is 1, minus 4, which is minus 3, equals a, we know is 1, and then times minus 1 squared plus 4, which is 5, so we're just going to get 5, plus b times minus 1, which is minus b, plus c, which we know is 4, times minus 1, which is minus 2. So we're going to get minus 3 equals 5, and expand the minus 2. So we'll get plus 2b minus 8. We get minus 3 equals minus 3 plus 2b. Then we get 0 equals 2b, and we get b equals 0. Which means we can rewrite this fraction as 1 over x minus 1 plus b is 0, so we just get 4 over x squared plus 4. So now we can find that integral a little easier, because we know it's the same thing as the integral of 1 over x minus 1 dx, plus we can write this as the integral of 4 over x squared plus 4 dx, and we just have to evaluate these integrals separately now. So here we have the derivative of the denominator as the numerator, so we're just going to get the natural log of the absolute value of the denominator. Now over here, this is very much looking like inverse tan, where we have x squared plus a squared, where a is equal to 2, and we just need 2 in the numerator, so we can take 2 out as a factor, and we'll get plus 2 times the inverse tan of x over a, which is 2, plus a constant. So have a look at another example. We have the integral of 0 to 1 of 3x squared minus 2x plus 1 all over x squared plus 1 times x squared plus 2. So again, we want to consider that fraction so we can decompose it into its partial fractions. So we're going to have 3x squared minus 2x plus 1 over x squared plus 1 times x squared plus 2. And since both of those factors in the denominator are quadratics, we know they need linear factors in the numerator. So we're going to have ax plus b all over x squared plus 1 plus cx plus d over x squared plus 2. So that's times everything by the denominator on the left-hand side. So it's just going to leave us with 3x squared minus 2x plus 1 equals ax plus b multiplied by x squared plus 2 plus cx plus d multiplied by x squared plus 1. Evaluating here, not going to go through it again, but the values of a, b, c and d, they're just going to be, a is going to be minus 2, b is minus 2, c is 2, and d is 5, which means this can all be written as minus 2x minus 2 all over x squared plus 1 plus 2x plus 5 all over x squared plus 2. So let's continue over here. So we're looking at the integral from 0 to 1 of minus 2x minus 2 all over x squared plus 1 dx plus the integral from 0 to 1, so we're breaking up into our two separate fractions, our partial fractions, 2x plus 5 over x squared plus 2. So let's look at these integrals. Now, here it looks like we still have a bit of a mess here, but we're going to break these up even further. So what we're going to do is we're going to say the integral from 0 to 1 of minus 2x over x squared plus 1 minus 2 over x squared plus 1. And we can do all of these integrals separately. Plus the integral from 0 to 1 of 2x over x squared plus 2, should all have dx, plus 5 over x squared plus 2 dx. So here we've got 4 integrals to evaluate. So just bear in mind that if you have 2 terms in the numerator, you can always break it up into 2 fractions as long as you keep the entire denominator. And all of these integrals should be a little easier to evaluate now. So over here, the derivative of the denominator is 2x, which we almost have up here. We just need to pull the negative out. So pulling this negative out, we get, then the integral of it is just going to be the natural log of the absolute value of the denominator from 0 to 1. Here, if we just pull the 2 out, we'll have an inverse tan as the integral. So we get minus 2 times the inverse tan of x from 0 to 1. Here our derivative of the denominator is in the numerator, so we can just straight away write that as ln of the absolute value of the denominator. And over here we look like we have an inverse tan, where we have x squared plus a squared, which means we need a in the numerator, so we need root 2 up there. So if you like, you can imagine putting a root 2 there, but then dividing by the root 2, and then pulling the 5 out the front. Which means that the integral is going to be 5 on root 2, and then the integral with the inverse tan of x over a, which is root 2, from 0 to 1. Then evaluating all of these with the 1s and the 0s, we're going to get minus, outside of ln, absolute value of 2, minus ln absolute value of 1, minus 2 outside of the inverse tan of 1 minus the inverse tan of 0 plus ln absolute value of 3, so subbing in 1 minus ln subbing in 0, absolute value of 2 plus 5 on root 2 inverse tan of 1 on root 2 minus inverse tan of 0. So here we're going to get minus, the absolute value of 2 is just 2, so we're just going to get minus ln 2. Absolute value of 1 is 1, and the ln of 1 is 0, so that's all column. Minus 2 times the inverse tan of 1 is pi on 4, minus the inverse tan of 0, which is just 0, plus ln of absolute value of 3 is just ln 3, minus ln absolute value of 2 is just 2, so we get minus ln 2, plus five on root 2, outside of the inverse tan of 1 on root 2, we'll just leave as that, and the inverse tan of 0 is 0. So let's tidy this up a little bit. So minus ln 2 minus ln 2 is minus, we'll write ln 3 first, then minus ln 2 minus ln 2 is minus 2 ln 2, minus 2 times pi on 4 is just minus pi on 2, and then we've got our plus 5 on root 2 inverse tan of 1 on root 2, and probably just tidy up this ln part. So we know from our log laws we can bring that 2 up to the front and make up to the top and make that 2 squared. And then we've got ln 3 minus ln 4, which will give us ln of 3 over 4 minus pi on 2 plus 5 on root 2 inverse tan of 1 on root 2 as your final answer.